Good morning to everyone. This is Mintupal here. So today in this video I'm going to solve a numerical which is based on the milling operation. Okay, and this is simply about me. So let's see. So here we can see that I will be solve a single questions only, but in that single questions I will be cover all these points. Okay, the maximum engagement angle in milling, then the angle between two consecutive teeth, number of engaged teeth, maximum uncut chip thickness, the maximum cutting force, maximum torque, then the average torque, and finally we will be cover the power consumption. So now let's see the question. So please pause the video and read the questions carefully. So in these questions, a mild steel block of 20 millimeter, okay, is being milled using a straight slab milling cutter. So this one is also important. Okay, straight slab milling cutter with 20 teeth. So number of teeth in that cutter is 20 and the diameter of the cutter is 50 millimeter. The radial rake angle provided 10 degree. The feed velocity of the table is 15 millimeter per minute. The cutter rotates at 60 rpm. If a depth of cut 1 millimeter is used, then we have to find first the maximum engagement angle, then we have to find the angle between two consecutive teeth, also we can say as an angular pitch, then the number of engaged teeth, then the maximum uncut chip thickness, maximum cutting force, maximum torque, average torque, power consumptions in this milling operation. And other informations are provided as the mu means the coefficient of frictions on the rake surface is 0.5 and the shear stress, or you can say the shear strength for the material as a 400 Newton per millimeter square. Okay, so let's solve these questions one by one. First, the maximum engagement angle. Okay, first, what do you mean by the maximum engagement angle? Let's say this is my milling cutter. Okay, this is my milling cutter. So how the machining is going on, and this is my workpiece. Okay, this is my workpiece. So this is my workpiece and this is my cutter. So this is the center of the cutter. You can see this is the zone, or you can see this much angle in which the cutter is engaged with the workpiece. Here or here the cutter is not engaged with the workpiece, but this is the angle in which the cutter and the workpiece are engaged. So this angle is basically known as the maximum engagement angle. Okay, so we have to find out this angle. Let me provide the name of this angle as a psi, and we are talking about the maximum, so psi m. Okay, the maximum engagement angle. So to find out the maximum engagement angle, there is a formula that sine of psi m is equal to 2 square root of our depth of cut by the diameter of the tool or the cutter minus depth of cut but by diameter of the tool by whole square. Now here actually we can observe this d is very small as compared to capital D, means the depth of cut is very small as compared to the diameter of the cutter. So and the for this square term we can neglect. Okay, we can neglect this square term and we can simply write this sine psi m as a 2 into root of small d by capital D. So now let's put the value. Small d here given, you can see 1 millimeter. So 1 millimeter depth of cut and the diameter of the cutter is 50 millimeter. Okay, so if you calculate this value, then you will get value around 0.28284. Okay, now we don't need this value, we need this psi m. So simply you can write the psi m is equal to sine inverse of this 0.28284, and from here you will get the angle around 16.4 degree. So this is the first answer of our question, that the maximum engagement angle. Carefully remember the name, engagement, that the angle in which the cutter and the workpieces are engaged with each other. Okay, and this is the angle. From the diagram also it is clear now. In this angle only the workpiece and the cutters are engaged with each other. So we have to find out this angle, and this angle is nothing but can be represented as a 2 of root of small d by capital D minus small d by capital D whole square. But due to this condition we can neglect this square term and only 2 root of small d by capital D, and we are putting this value and we are getting the value of maximum engagement angle as a 16.4 degree. Okay, so and in this diagram this is the value of D. Okay, this is the value of small d. Now next question, angle between two consecutive teeth. Okay, this one is also very interesting question. Angle between two consecutive teeth. Let's go to the next page. Let's see, this is my milling cutter, correct? Please ignore the drawing. So here in this milling cutter, in this periphery we have number of teeth, correct? We have number of teeth. So in this question they ask, what is this angle? Let's say here one teeth and here one teeth. So the angle between these two consecutive teeth we have to find out. Okay, we have to find out this angle. This is a question number 2. Okay, so you just think it is called a, you can see also, say also this is a angular pitch. Okay, let me represent by this. Now what is the angular pitch? Now this 360, okay, total the diameter means the total how much angle is there, 360 angle is there. So this 360 angle covered by how many teeth is? So number of teeth, think by Z. So here the number of teeth is 20. Okay, here the number of teeth is 20. So this is the angle between two consecutive teeth. Are you getting my point? We have total 20 number of teeth. So this total 20 number of teeth covers how much angle? 360 angle. Throughout the periphery all the teeth are present. So 20 teeth cover 360 degree angle. So just we have to find out that what about the angle between two consecutive teeth. Then this is 360 by, sorry, this is not 20, 360 by 20. So this is actually I write here. So this is the second question simply. Now the third question is number of engaged teeth. Now listen. Previously in the first questions we calculated whatever the angle engaged between the cutter and the workpiece, and we also know what the angle between two consecutive teeth. Now in third we have to find out the number of engaged teeth. What is the total engagement angle? This is my total engagement angle. And what are the angle between two consecutive teeth? This, correct or not? So if I divided this two value, that we have the maximum engagement angle psi m, but in that maximum engagement angle, let me draw it properly, then you will get the better idea actually what angle or what point I am talking. Let's say this is my milling cutter. In this milling cutter, this is my workpiece. Okay, this is my workpiece. So this is my psi m, correct? This is my psi m, maximum engagement angle. This portion is engaged now, so the angle between this point to this point is my maximum engagement angle. But let's say this is the point. Let's say here one teeth is present and another teeth is present here. Okay, then what is this angle? This angle is my psi, this epsilon, correct or not? Are you getting my point? This total from here to here is my maximum engagement angle, and the angle between two teeth is this value. Although in this case we have this value greater than this value, so this psi value actually we have to draw. Psi is here, but this zeta will be somehow here because this zeta is greater than the psi. So this is our actually here 18 degree, and this value is our here something 16 point, I forget 16.4. This is my 16.4. So I hope it is clear. Now if we divided it, will we get some value, and it is here less than 1. So what we can say, how many teeth are engaged at a time? One teeth is engaged at a time, single teeth. Getting my point? Let's say this value is suppose greater than 1. Okay, something, let's say 1.6 or something like this. So in this case the two teeth are engaged at a time, correct? So in this case the how many number of teeth are engaged? One teeth is engaged. What is the fourth question? Maximum uncut chip thickness. Okay, now we have to find out the maximum uncut chip thickness. Let's say I am representing it by AM. Okay, maximum uncut chip thickness. There is a basic formula we all know, that for turning actually we remember it, that maximum uncut chip thickness is S0 into sin phi, correct? Where phi is the principal cutting edge angle and S0 is the feed in millimeter per revolution. Here also you write the same equation. Okay, like S0 feed, here the feed will be feed per teeth, and this sin phi will be replaced by sin psi m. Okay, sin phi will be replaced by sin psi m, and remaining things will be as it is. Now we have to find out the feed per teeth. How to get the feed per teeth value? Actually we have one value, table feed. Okay, this feed is actually in millimeter per minute or maybe meter per minute, but with respect to time. So this is the table feed. Table feed can be written as a feed per teeth into number of teeth into the rotation in the what is the speed of the cutter. So we have to find out the ft, simply f by z into n. In this case our table feed was provided as a how much? 15 millimeter per minute. Table feed provided as a 15 millimeter per minute, z provided as a 20, and the rotation given as a 60 rpm. Okay, this is as a 60 rpm. If you put all these value, you will get a value. Let me calculate it. 15 by 20 into 60, around 0.0125 this much millimeter per tooth. Okay, this is the value of feed per tooth. So you can directly put this value here, 0.0125. now this sin psi m, if you carefully observe, this is the sin psi m, already we have the value 0.28284. so, or if you want you can write also 2 into small d1 capital D 50. You can remember sin psi m was 2 into root of small d by capital D. Okay, so this value actually I write here, and after getting, and this 0.0125, this is 0.28284, because already we calculated this value. Now if I multiply this two value, 0.28284, I'm getting around 3.5 355 10 to the power minus 3, this much millimeter, or also you can write 0.0035 millimeter. Okay, so now we have the maximum uncut chip thickness. Okay, so next what we have to find out, question number 5, the maximum cutting force. Okay, so question number 5, maximum cutting force. Let's say P, for this P is the force, and let's say this is the maximum force. Okay, or whatever you can represent. Sometimes it is also represent like PT and maximum cutting force. Now there is a basic formula for the cutting force, irrespective to the drilling, milling, or the turning. There is a simple, the shear area into shear stress into cos of eta minus gamma naught by cos of eta minus gamma naught plus beta naught. Here what is the eta value? Eta, gamma naught and beta naught. Beta naught is shear angle, gamma naught is orthogonal rake angle, eta is the angle between, or the angle between, or frictional angle between coefficient the frictional force and the normal to the frictional force. Okay, now this shear area is your uncut chip thickness by sine beta naught into your width of the chip. These two things. Okay, the uncut chip thickness by sine beta naught into width into shear stress as it is cos of eta minus gamma naught by cos of eta minus gamma naught plus beta naught. Now we have all this value. Okay, the AM maximum chip uncut chip thickness we have 0.0035. let's put it here, 0.0035. Width, in question width also given, we can see width is 20 millimeter. Okay, width is a 20 millimeter. Sine of beta naught. How to find out this beta naught? The given value mu is equal to mu value provided as a 0.5. so we know that tan inverse of this mu is nothing but my eta. So if I find this value, that tan inverse of mu, I'm getting around 26.56 degree. So we have the eta value. Also in question it is provided that the gamma naught as a 10 degree. Actually they are providing the radial rake angle gamma r, but for milling the radial rake angle and orthogonal rake angle both are same. Then next is we have Lee and Seyfert equation. Lee and Seyfert's equation, that beta naught plus eta minus gamma naught is equal to 45 degree. So from here you can put the value of eta, you can put the value of gamma naught, then you can find out the beta naught value as a 45 minus eta as a 26.56 and plus gamma naught is 10. So from here you will get the value of beta naught. Let me find out. 45 around 28.435 degree. Okay, this is the value of beta naught. So you can put this value here, 28.435, and this shear strength also provided 400 Newton per millimeter square. Now cos of eta minus gamma naught, eta is 26.56 minus gamma naught is 10, and this value is cos of simply 45 degree. Okay, because this is, you can see, according to the Lee and Seyfert equation, eta minus gamma naught plus beta naught is 45 degree. So directly you put this value. So from here, if you find out the total, the maximum cutting force, you will get the value around 79.72 Newton. Okay, now Newton. So this is my answer of fifth question. This is actually my maximum cutting force. Okay, now the sixth question was the maximum torque. Simple thing now. Let's say torque represent the T represent the torque and the maximum. So maximum torque is our maximum force into diameter of the cutter by 2. Simple things. We have this value as a 79.72 and we have the cutter as a 50 by 2, but this cutter unit is, this diameter unit is in millimeter. We have to convert it into meter. Okay, so if we calculate this value 7.9 to 79.72 into 25 divided by 1000, so I'm getting around 1.993. You can take it approximately 2 Newton meter. Okay, you can take it as a 2 Newton meter is the value of our torque. Okay, this is the answer for our sixth question. Let's go to the question number 7. Maximum torque. Till now we covered. Now the average torque and the power consumption. Okay, good. So now the question number 7 is the average torque. Okay, listen, let me draw a torque diagram in milling. In this direction we have the psi m value. This is the psi value. You can also see the rotation. Actually here we have the rotation in angle degree, in terms of degree, sorry, not degree, degree, and here we have the value of torque. Okay, now if you carefully observe, in this case this diagram can be actually vary, depends on our case, and the case is how our psi m and epsilons are related. In this case we found that our psi m is less than epsilon in this case. Now it may be, this is the, let's say, first case. Now second case may be like this. This can be equal, or this psi m can be greater than this epsilon. These two also possible. So in this video or in these questions, this is our case. Okay, means how initially there is no torque because no engagement of teeth. Now when the teeth start to engage, torque start to increase. Although here I am considering it as a straight line, but it is not actually straight, but let's say considered for our better calculations or easy calculation. So we are taking it as a straight line. So then this torque will be come down because after a certain angle there will be no, again there will be no engagement of teeth to the workpiece. So that time also we will be have a zero torque. Okay, then again up to certain time there will be no engagement, and again once more teeth will be comes to engage with the workpiece, and it will be once again create some torque and once again it will be come to the 0, and this way this diagram will be continue. Okay, continue. Now here one thing you can observe, this is the value called the maximum torque. Okay, and what is this value? Up to this actually our maximum engagement angle psi m. Okay, but this value is our epsilon, means angle between two teeth. You can see one teeth comes in contact to the workpiece, it creates some, as a result we are getting some torque. Then finally once more teeth when comes, then again that we are getting some torque. But in this gap no torque, because there is no engagement between the cutter and the workpiece. And the reason here this psi m is less than the epsilon. If it is equal, then this psi m will be comes to here, the diagram will be start from here, this will become something like this. Okay, because both are same. So later in other video I will be discuss about it. So here this is the scenario. Now this is my maximum torque, and let's say this is my average torque. So actually in this diagram, this area, okay, let me very clearly draw it. So actually this area equal to my this area. Are you getting my point? Means what I can write, simple, this area I can write as a area of a triangle, correct or not? So half of my maximum torque into this psi m. Similarly this area as a area of a rectangle, this is my average torque. So average torque into this, correct or not? So now I have all this value of maximum torque around 2, this psi m around 16.4, this we have to find out, and this value around 20. Now from here if you find out, you will get the value around 0.91 Newton meter is the value for our average torque. So this is the actually question number 7. Now the question number 8, what is the power? Okay, so power is nothing but our torque into omega. Now the question is that what torque we have to find out. We have to consider the average torque. Okay, average torque into omega. So average torque is 0.91. What is the omega value? 2 pi n, and here n is 60 rpm. As it is this value in rpm, so we have to divide it by 60 to convert it into rps divided by 60. Okay, to divide it. Okay, now this 60 get cancel out. So 0.91 into 2 into pi, 0.91 into 2 into pi. So we are getting around 5.7177. Okay, this much watt. Or for your better, you can equate to as a 6 watt also. Okay, so this is actually the power. Okay, so in these questions, let's say here I write down up to 1 to 7 whatever the questions are present here. Actually if directly the power actually asked to you to find out, then also you have to go through from question 1 to question 7. Okay, because you can observe here how the each and every questions link to the other. First we have to check, actually directly we have to jump to this third question, actually, what are the number of engaged teeth? First we have to check it. Okay, so to check this we need the maximum engagement angle and the angle between two consecutive teeth. This is the maximum engagement angle, this is the angular pitch, and then from here I can find out the number of engaged teeth, because this number of engaged teeth providing you the information that in this machining zone how much teeth are present, because based on that only we can draw our this diagram, and from this diagram we can find out the average torque. Correct. So actually all the values whatever I calculated here all are linked to each other. So you have to go through from question number 1 to question number 7 to find out the question number 8, means the power value. So I hope in these questions I give you some informative value. So if you really think that, then please like my video and subscribe my channel. So in this video this much only. Thank you for observing my video. Thank you so much.